There is a chance that you are going to be assigned a problem, a homework problem in Chapter 8 associated with reheating the steam as it exits the high pressure section of the steam turbine, goes back to the boiler to be reheated, and then back it comes to an intermediate or lower pressure steam turbine. That is a way to improve the thermal efficiency of a steam power plant. So I want to give you some tips on what is going to be different about a more complex steam power plant with reheat than the traditional basic Rankine cycle. Okay, so we covered some topics of regeneration, which would be feed water heating. This is a totally different animal where you're working with the steam. You're reheating steam. Okay, and so the chances are good that you're going to have a homework problem like this. And I want to point out some fundamentals about analyzing this process that many students simply don't grasp, and understandably, right? So there are some details you have to study very carefully to fully understand what's going on here. Well, of course, tried and true copy and paste slide, right? You know by heart the four major components of the Rankine steam power plant cycle. I don't need to tell you those. You know them by heart now. You know how they fit together. And you're getting pretty good at analyzing them, I hope. And of course, you're pretty good at drawing the TS diagram of the basic Rankine cycle. And just visually, you can identify, well, which component applies to each of these four processes. You're pretty good at that. Okay, well, now I've taken a screenshot from the homework problem that you're probably going to be assigned. I've simplified it a little bit. But I want to point out, so let's look at the sketch. So you'll be provided with a sketch. Let's see what we've got. The top upper left, here's our steam generator, our boiler. And so the tried and true starting point is remember, we've got our feed water pump. So we're coming into the boiler at state 6, and we're coming out of the boiler at state 1. Now, a little picky point, of course, is that remember, we're adding heat. I like this schematic here of the generating bank of the boiler, where the circle would represent a steam drum, but do recognize we're superheating the vapor. We're adding heat in this little section right here called the superheater section, and it's going off to the high turbine 1. That would be the high pressure turbine. Okay, now we're going to get a little more complicated. It's coming out of the high pressure turbine. And I think in your homework problem, this is going to be a reversible and adiabatic turbine, I believe. Okay, reversible. So you have the ability to analyze the reversible adiabatic turbine to determine state 2, as long as you're given that pressure. And you will be given that pressure state 2. But notice here, we're not going into turbine 2 immediately. We're coming back through piping back to a reheater. We're coming back into the boiler to a reheater, and we're going to be heating it back up to a given temperature and pressure. Well, P2 is going to equal P3, a given temperature, and it's coming back to be admitted into the inlet. I don't like the sketch coming into the middle of the turbine. It should be coming into this front end of the lower pressure turbine, but we'll forgive the author for that. Coming in at a known pressure and temperature turbine 2, and coming out of turbine 2 to state 4 to the familiar condenser where you're rejecting heat to TL. Okay. Let's see, state 5 is going to be saturated liquid back to the boiler feed water pump, and you've gotten pretty good at analyzing all of those. What I want you to do is observe that the path I just discussed is a serial flow path. There's no splitting of the flow. It's one serial thing. So let's go over it again. I've got state 1 coming out of the boiler. It's going, state 1's coming through turbine 1, coming back, state 2 to the inlet to reheat, still the same flow. State 3, still the same flow, coming into low pressure turbine. State 3, out of turbine 2 at state 4, still the same flow, into the condenser, State 5, same flow. And so it's kind of key to recognize that all these M dots are identical. They're all the same. Okay. A lot of students don't get that because they've had previous homework problems on regeneration where there's this Y stuff and gosh, and so they think this is going to be similar. This is actually much simpler. Oh, but then the important part here is in your analysis of thermal efficiency, remember, what was thermal efficiency? What was that in words? Energy sought over the energy that costs. And where's the energy that costs? That's the money that you have to spend to buy to support this high temperature heat source. And so for this problem of reheating the steam, do you see that you've got two places where you're adding heat to the H2O? Two places. That's the key. That's all you got to remember. There's two heat addition places that make up Q dot H in your thermal efficiency statement, the denominator. That's all that's different. All right. So what's the benefit of reheating turbine one's exhaust steam? The benefit is that you're reducing the heat transfer across a finite temperature difference. You're going to be improving the thermal efficiency. So do you see that by reheating, you're going to get more power out of your turbine too, because the enthalpy has been bumped up. So if you didn't reheat the steam, you'd be going into turbine 2 at state 2, but you're reheating the steam, you're adding more heat. So you're increasing the enthalpy at state 3, and so you're getting more power out of your lower pressure turbine than you would have otherwise. So now what's the TS diagram going to look like for this situation, right? Do you see that it is similar to the basic Rankine cycle? So here's our turbine 1. This is our high pressure turbine. So it's going in and it is expanding down to a lower pressure to state 2. We don't exactly know where that state, you won't know where that state 2 is until you do the analysis, okay? But it's coming out at state 2 at a known pressure, a given pressure. You're going back into the boiler. And so this process 2 to 3, this constant pressure process 2 to 3, that's the reheater process. So you go back into state 3, and my memory is that we're reheating the steam right back up to T1. That's my memory of your assigned problem. T3 is going to be exactly equal to T1. Then you go into turbine 2, and look at all this extra power you get. So do you see that if you did not reheat your steam, you'd be going down this line, 1 to 2 to 4. But since you've reheated, you're going from 3 to 4. So look at that extra amount of turbine power you're getting. So you're getting more turbine power. You're adding more heat, but you are reducing the heat transfer across a finite delta T. Okay, back to, and what would this look like in the world? Well, I think here's a picture of our boiler furnace. You do see that I've shown, here's my steam drum where I've got saturated vapor coming out of here. And then you've got a superheater section going into state 1, very similar to the textbook sketch, okay? Coming back from turbine 1 into a reheater, out of the reheater up to T3, into the turbine 2, the lower pressure turbine, and then state 4, the condenser. And what will this reheater section look like? It's simply going to look like a bunch of hairpin tubes connected up to a couple of manifolds, an inlet and an outlet manifold. And that's what that reheater is going to look like in the horizontal position. And that's sort of what it's shown like in this sketch. So that helps you maybe hook up a textbook sketch to what things would look like in the world here. What's the first law going to look like, energy balance, for the reheater? Let's see. Steady state, steady flow, one inlet, one outlet. We're going to say that there's no changes in potential or kinetic energy. If we've designed our reheater well enough, there's going to be very minimal pressure drop across our reheater for the H2O. So P2 is going to equal P3. Do we see the reheater lifting a weight? No. Do we see a shaft coming out? No. So W dot out is going to be 0 for the first law. And Q dot in, that's what we're looking for. Q dot from in from 2 to 3. Q dot in from 2 to 3. That's simply going to be M dot 2 times H3 minus H2. Good old first law. Enthalpy out, enthalpy in, M dot. Units, kilowatts, or BTUs per hour. So that's the way you determine the heat added for the reheater only. Okay. And so how do you get H2? Well, you've got to analyze turbine one. Let's see, S2 equals S1. So you're going to need to determine H2 from the isentropic analysis of turbine one. That's the way you get H2. And H3 is basically going to be given to you, isn't it? Because you're going to be given the pressure, P2, and you're going to be given T3. You have to know how hot you're reheating the steam to. So if you've got P3 and T3, it's simply a matter of looking up in your superheated steam tables to determine H3. So that's really very easy, right? And so, right, so what's the hard part? The hard part is putting it together when you're asked to find the thermal efficiency of the overall power plant. And so just this is a reminder that I've already talked about. Heat is added in two places. And so your Q dot H, that's different than just the reheater heat added, isn't it? So here's the statement of the first law for the entire steam generator. So let's see, entire steam generator, steady state, steady flow is going to have, let's see, 1, 2 inlets, and it's going to have 1, 2 outlets. Okay, so you're good with the first law, 2 inlets, 2 outlets, steady state, steady flow. Let's see, Q dot H, it's going to be made up of minus W dot out, well, that's 0. Well, M dot 6 times H1 minus H6, so you can kind of see that with your eyes. It's the mass flow times outlet minus inlet enthalpy. And then also M dot 6 is the same up here, right? It's a serial flow. Everything's flowing in series, so we can just put M dot 6 there instead of M dot 2. And then out minus in, enthalpy out minus enthalpy in. I hope you've got this first law nailed for open system, multi-inlet, multi-outlet. So, boy, I hope you've got that nailed. And you say, I think I'm catching on to this, and maybe I see why I'm being assigned these difficult problems because it's giving me repetition on using the first law to analyze thermal systems. Okay, I hope that helps you set up your homework problem when you're assigned a steam power plant with reheating the steam.